Hey there, deep learning enthusiasts, data scientists, and data engineers. Welcome back to the channel where we make complex concepts crystal clear and exciting. Today, we're diving into one of the cornerstones of neural networks, the Rectified Linear Unit, also called as ReLU. So, whether you're just getting started in machine learning or looking to strengthen your understanding of activation functions, this video will take you from what is ReLU to how does it work. Here's what we will cover for today. So, we will be having a breakdown of the theory and magic of ReLU. We will also have a basic coding implementation of ReLU to see it in action. And also, we will be having an advanced neural network implementation showing how ReLU powers deep learning models. Get comfy because this is going to be insightful and fun ride. Let's get started. All right, let's start with the basics. Picture this. You're designing a neural network, a model that mimics the human brain by learning patterns and making decisions. But there's the catch. Neurons in this network needs to decide, should I activate or stay quiet? Enter the activation function. ReLU, one of the simplest and most widely used activation functions, answers that question beautifully. So here's the formula. It's actually very simple. The function of x is equal to the max 0 and x, or from 0 to x. So what does this mean? It's actually very simple and very straightforward. If the input x is greater than 0, ReLU says just keep it. And if x is less than or equal to 0, ReLU says, okay, let's make it 0. So think of it like a positive vibes filter. So it keeps the positive signals and discards the negative. And because of the simplicity, ReLU introduces non-linearity into the network, and this allows it to learn complex patterns. So without activation functions like ReLU, neural networks would just be glorified linear equations that is incapable of capturing the real-world intricacies of data. Of course, the world is not simple, it's actually very complex. So why do data scientists and data engineers and AI engineers absolutely adore ReLU? So here are two big reasons: efficiency in training and sparse activation. So efficiency in training. ReLU is lightning fast to compute. So unlike older activation functions like sigmoid or tan8s, ReLU doesn't compress the values into a narrow range. It avoids the infamous vanishing gradient problem. So which means to say that the network keeps learning even as layers get deeper. Sparse activation. So in most layers, only some neurons output non-zero values. So this sparsity reduces computational effort and makes the network more efficient. Imagine an office where only the right people work on tasks while the rest stay on standby. That's what ReLU does for neural networks. But of course, ReLU is not perfect. There are challenges, and these are the two of some of them. And so far, these are the most famous ones. So dying neuron problems. And also we have gradient at 0. So if a neuron's input is consistently negative, it outputs every time and effectively dies, so contributing to nothing to the learning process. So it's like having a teammate who is permanently disengaged. Frustrating, isn't it? Gradient at 0. So technically, the gradient at x equal to 0 is undefined. But don't sweat it. Modern frameworks handle this gracefully, so it's rarely an issue in practice. Now that we understand the theory, let's jump into some hands-on coding and see how ReLU goes in action. So let's go there. All right, let's start simple. So just imagine you're working with a small data set, just a list of numbers that are positive, negative, or even 0. So you want to apply ReLU to this data. So here's how you would do it in Python. So we have here just a list of numbers, and we have the blank container. which is named output. So let's execute this one and see what we have in here. So this code just iterates through each value in the inputs list, as what I've mentioned. So what this means is that if the positive value can be seen, the code just keep it, the program just keep it as it is. So if it's 0 or negative, it replaces it with 0. So now we have these values that you can see. So 0 now is just 0. Negative 1.3 is 0. Negative 2.7 is 0. And negative 10 is 0. And all the rest positive values are just as is. And this one is just a simple implementation or the other way of implementing this simple implementation of ReLU. Let's see what this would come up. Okay, so as you can see, we have the same results, of course. So ReLU is working exactly as expected. It's retaining positive values and filtering out the negative ones. But there's the thing, this approach works only for small data sets. So what if you're working with thousands or even millions of data points or multidimensional data like matrices? So that's where we need to have a more advanced implementation. And so we need to have some kind of level up. So let's level up, ladies and gentlemen. Now let's look at how ReLU powers real networks or real neural networks. And this is what I've said. So now we'll create two classes. So we have layer dense and we have activation ReLU. So layer dense class actually represents a dense layer in the network with weights and biases. This is actually what we talked in our past lesson prior to this lesson. Activation ReLU, this applies the ReLU activation function to the outputs of the dense layer. So here's how we do this one in Python, as you can see here. All right. So the setup simulates a neural network layer. The layer dense just initializes weights and biases. And then the activation ReLU class applies ReLU to the layer's outputs. So now let's generate some data through it or through our neural network. But before that, let's first execute this one. Okay, now that it is executed, we can now execute this. Let's see what will happen after. Okay, so this code generates a spiral-shaped dataset using the nnfs. So we are just making our life simple in this case. So we are generating the data from this package or library. So this creates a dense layer with two inputs and three neurons, as what we already have set. So two inputs and three neurons. And then we apply the ReLU, this one, the ReLU activation function. So the first 10 outputs look like this. So we have just actually generated only the first 10 outputs. But of course, we can also do more than 10. So here's what's happening. The dense layer computes the weighted sum of inputs, and the ReLU replaces this one all negative values with 0, keeping the positive values intact. So this is how ReLU operates in a real world neural network. So as you can see, there are no negative values in this case. So let's make this one 20. So no negative values. All right. So, and there you have it. A deep dive into a rectified linear unit. We covered the theory of behavior, or the theory and behavior of ReLU, a basic implementation of ReLU for beginners, an advanced neural network implementation for real-world applications. So ReLU may look simple, but it's actually a powerhouse that makes deep learning possible. So whether you are working with image recognition, text analysis, or even other complex tasks, ReLU helps your models learn efficiently and effectively. So if you found this video insightful, hit the like button, subscribe to the channel, and let me know if you have some comments. What topic you would like to see next. Until next time, keep learning, stay curious, and have Have a happy coding.
Do you want to know more about this channel? Just click these cards. We do have a lot of free data science courses for free like Machine Learning Essentials, Deep Learning Mathematics, and a lot more. Here, you can always learn an upskill for free.